All right, so welcome back. This is an ALEKS topic that's called predicting the relative boiling points of pure substances. This is a really good ALEKS topic. The point of this topic is really to talk about intermolecular forces. So you might not get that, right, from looking at this problem. There's no mention of intermolecular forces, but at the end of the day, that is really what is most important about this problem and how we're going to solve it, essentially. So the relative boiling point, that's actually going to be related to the intermolecular forces, because the more intermolecular forces, the more stuck together our substances are, the higher the boiling point is. So the boiling point is really just sort of a measure of what the intermolecular forces are. So a higher boiling point means more stuck together, means more intermolecular forces. So then we need to think about our different intermolecular forces, that are going to be at play: dispersion forces, dipole-dipole interactions, and then obviously hydrogen bonding. And in this problem, I'm going to go through a variety. I'm going to go through 3 different examples of the same problem. So let's go ahead and get into it. So the first one here, we're asked to rank the elements for, I guess all of them, we're going to be asked to rank the elements from the highest boiling point. So number 1 means highest boiling, most stuck together, and then number 4 will be the least stuck together. And when I look at these different substances that I'm given here, sort of two things jump out at me: that A and C are very similar, and that B and D are also very similar. So then I'm going to compare basically B and D. I'm going to compare A and C, and then I'm going to compare how do these species compare to things like B and D overall, to sort of figure out what my overall ranking is. The one that I would probably start with is B. So B, N2, I could go ahead and draw a Lewis dot structure for N2. It's nonpolar, it's small, we're only going to have dispersion forces. This is going to be the least stuck together. So when I'm ranking the different things, the things that I'm going to be sort of thinking about, number 1 will be size, and then number 2 will be intermolecular forces, IMFs. So the size is really going to be related to the intermolecular forces because of dispersion forces, but that's going to be the first thing that I sort of look at. So N2 and NO, they're roughly the same size. N2 is going to be nonpolar, therefore it's not going to have any dipole-dipole interactions or anything like that. But NO is going to be the next one. So NO is also relatively much smaller than our other molecules here, right? I've got multiple carbons and oxygens, multiple carbons and nitrogens and oxygens. So NO is going to be the next one, simply because it's small compared to these 2 other things. So as you get bigger, you're going to get more dispersion forces, you're going to be more stuck together. So now I need to decide between A and C, and the thing that jumps out at me is the potential here for hydrogen bonding. So I'm actually going to draw in a hydrogen bonding interaction with this molecule. We could actually draw a really nice one here. So N, H, H, and then C, O, H. So I've drawn another molecule of the same type interacting with this molecule here, and these interactions here, these are going to be hydrogen bonding interactions. Hydrogen bonding. So we would say that this molecule can hydrogen bond with other molecules of itself, like itself. That's going to be a really strong interaction. That's going to mean that it's really stuck together. So sort of by process of elimination, this is going to be the most stuck together. That means that this one will be next. Here we're going to have a dipole-dipole attraction with this C double bond O. But this molecule cannot form hydrogen bonds with itself. It could form hydrogen bonds with water. I could have a water molecule here, but this molecule does not have oxygen bonded to hydrogen. Therefore, it cannot hydrogen bond with other molecules of itself. So this is going to be, less stuck together than this one here. Let's do some more examples, and hopefully we'll illustrate a few other things. So I've got 2 more examples to go through here. So in this one, make sure we can see everything. That's nice. The first thing that jumps out at me is aluminum oxide. That's an ionic compound. And ionic compounds are going to be held together by actual positive and negative charges. The root of our intermolecular forces, London dispersion forces, dipole-dipole attractions, those are really sort of partial positives attracted to partial negatives. Well, here we have actual positives attracted to actual negatives. That's going to be much more stuck together. So right away I can say that one's going to be number 1. And then I might go, to the other side and say, well, here I've got O2. O2 and CO, those are going to be very small. This is going to be somewhere in the middle. So I think that I could say, well, let's do this comparison, O2 and CO. O2 is going to be number 4. Just like we talked on the other slide about N2, We've got a small nonpolar molecule. CO is going to be next. Here I've got dispersion forces and dipole-dipole attractions. If you think about the structure of CO, I guess we could just draw out a Lewis dot structure. Our Lewis dot structure for CO, this is going to be a polar bond, partial negative, partial positive. We could have dipole-dipole attractions between this CO molecule and another CO molecule and another CO molecule, so on and so forth. So that's going to be more stuck together than the O2. Now this one here, our C2H6O2, looks like, this is a little bit bigger, right? So just based on the fact that this is bigger than our CO or our O2, tells me that it's going to be more stuck together, right? As it gets bigger, more dispersion forces, therefore more stuck together. So we already know this is going to be 2 based off process of elimination, but I do want to point out that this would be able to form hydrogen bonds with itself. So I've got OH here. That indicates I could have another one of these molecules hydrogen bonding with this one. And we could actually draw that interaction here. So OH. And this interaction here from the lone pair of electrons to this hydrogen and here, that would be a hydrogen bonding interaction. Here I'm showing sort of 2 hydrogen bonds stacked on top of each other. It doesn't have to be like that. It's just an easy way for me to show that. Okay, one more example and we'll be done. So in this example, let's make sure we can see everything. So in this example, we've got F2, jumps out at me right away, small, nonpolar, that's definitely gonna be number 4. And now I've got a sort of a variety of different things to be looking at here. So these two, obviously they look very similar. I'm gonna be doing a direct comparison of these two. And then this NNO, this one is a little bit smaller in size than these two. So just based off of that, I'm not even gonna think about really anything except for what's the size of NNO versus the size of these larger species. Since this is smaller, that's going to be number 3. When we're doing our comparisons, we want to try to make as direct comparisons as possible. And the fact that this is, smaller in size than these, it's going to have much less dispersion forces. That's going to mean that it's less stuck together. So that's going to be number 3 in this case. Now between these two, I want to be thinking about dipole-dipole interactions, hydrogen bonding. Obviously, both of these are going to have dipole-dipole interactions because of this C double bond O. This is a polar bond. So we would have a polar, bit to our molecule here. But really what's important here is this NH bond here. So this right here, this indicates to me that this molecule can hydrogen bond with itself, with other, I'm going to write like molecules. So other molecules of this substance can form a hydrogen bonding interaction because I've got the nitrogen bonded to hydrogen with a lone pair of electrons. I could set up another hydrogen bonding interaction. I do not have that here, right? Because I do not have oxygen bonded to hydrogen, this molecule here will only have dipole-dipole interactions. So this is going to be number 1, and this is going to be number 2. So I want to make sure I got those straight. All right, hopefully that helps. Definitely let me know if you've got any other questions or any other ALEKS topics that you'd like me to make videos for.